Okay, fantastic. So, good morning for those joining us from Australia and New Zealand. Good afternoon, good evening for those elsewhere in the world. Currently, I'm in the UK, so we are just after 10 p.m. in the evening. But very warm welcome to this first in six series of webinars. I want to kind of crack on with the material as soon as possible, so I'm going to keep the introduction fairly brief. My name is Rob Green. I am a Hydronic college trainer based in the UK, looking after in countries including Australia, New Zealand, Middle East, and Asia. So I have been in the industry now for around about 15 years, specialising in manual balancing and all things kind of hydronic system based. Before we kick into the technical material, I just want a little bit of housekeeping to clear up some of the sort of fairly regular questions. We will be recording this webinar, so we are recording live now. So as you've joined, or if you are yet to join, you will get access to this recording as part of the Teams webinar setup. And you'll notice your mics and cameras have been disabled during the webinar. So you will not be able to be on screen, and we will present. Hopefully this should be about 45 minutes of presentation, and then we will have some time at the end for some Q&As. Again, also slide pack will be available as a PDF for attendees that we will send out to all attendees, so you don't need to worry about that. And in the webinar, I'd like to ask you if you could use the Q&A section. So at the top of your screen on Teams, you should hopefully see a little area where you can go to chat and Q&A. If you click on the Q&A, this window will appear, and you can then start to create posts, start discussions on Q&A there. Unfortunately, it's only myself on the IMI technical staff on board today. So what we'll do is at the end of the webinar, I'll collate all of these questions and hopefully we'll be able to give you some answers. If we can't, we can come back to it another time. That's not a problem at all. But without further ado, let's have a look at what we're going to be learning about today. So on the agenda for today is we are going to start this webinar with an overview on balancing, kind of why do we balance, what's the importance of it, and just a general overview on system commissioning and balancing. We're going to move on then to looking at some of the main sources of imbalance. Very briefly, as I said, this is about a 45-minute webinar with the idea being an introduction to these topics. We do lots of courses on this that are in the ranges of days and weeks. So we're going to kind of cover as much material in this start here. We're then going to look at the most important relationship in hydronics, which is the differential pressure versus flow in a system. And I'm going to introduce or re-talk about, if you've learned about it before, something called the proportional law, which is another really important topic when we are in particular looking at manual balancing and understanding how flow and pressures are working in systems. The proportional law is extremely important to us to be able to exploit it to ensure we can effectively commission a system. And actually the webinar we're going to do in next month is going to look at some of the ways we can run some advanced commissioning techniques. And finally, last but not least, is a design consideration side where we're going to look at actually the best way of breaking up a system into what we call hydronic modules. So let's have a start by looking at an overview on balancing itself. And I want to start by talking about the HVAC system, excuse me, the HVAC system in general. All HVAC systems need to reach two fundamental objectives. We want to deliver the specified comfort level, the indoor comfort level we require in our rooms, in our buildings. And we want to reach that first objective while using the minimum quantity of energy. Now, objective number one is, you could argue, a design objective. We need to make sure we select the correct components to ensure we can get sufficient cooling or heating throughout a building. And number two is really where manual balancing takes a role, because that's where we can ensure we are doing it as efficiently as possible. We're only using the flow we need. We aren't going with excess flow on the pumps, excess pump head, all of these things. And commissioning is going to play a vital role in achieving this, because to get that second one, the system must be set up correctly. And in reality, where we're looking at really with the commissioning is this distribution side. How are we distributing the flow throughout an HVAC installation to ensure all areas are satisfied and they are only satisfied to their minimum requirements? We're not over satisfying, we're not overcooling or overheating. And often we can say, well, why do we need to balance? Why should we balance? And let's have a look at a fairly typical building, a high-rise building here. And if we did no balancing at all, water is fundamentally lazy. So without hydronic balancing, what's going to happen? My first circuits closest to the pump are going to be in overflow. And if we have a defined amount of flow in the system, which is a function of the differential pressure this pump is producing, we will end up with underflows in other areas. So the more extreme areas hydronically in the system are going to be in underflow. And underflow is going to cause underheating or undercooling if we're looking at a cooling installation. So we're not going to have a comfortable indoor climate, for number one. And control valves themselves, we're going to look about control valves in a few sessions time. But fundamentally, control valves do not solve this issue. Yes, a correctly set up control system should be compensating for excessive flow and excessive output from my emitters, but it's going to take some time to do that. And we're going to need to be ensuring we are correctly proportionally balancing this water volume to get the right flow to the areas we need in the system. And in the simple terms, in heating, an underflow is going to be too cold. We aren't going to have sufficient heating. And an overflow, we're going to be too warm. And that's going to be the vice versa if we're looking at a cooling system. Too much flow in a cooling system, too cool, not enough, too warm. And actually, if we look at what we call the cost of discomfort, so often, typically in an unbalanced system, we will lower our set points in cooling. And actually, or raise them in heating, because we want to be comfortable. And we say, well, hang on, it's cold in this room, so I'm going to raise my set point. Yes, my set point should be 20 degrees, but I'm going to raise it to 21 degrees. And you can say that's only 1 degree, Rob. It's not a huge amount. But actually, if we take a heating system, we can look at 6 to 11% of additional energy consumption for just 1 degree too high room temperature in winter. So if we've poorly balanced my system, and to compensate for that, we're going to up my set points, we can be looking at running 6 to 11% of additional cost energy consumption in that plant. It gets even worse with cooling. For 1 degree too low room temperature in the summer, so typically I spend a lot of my time in hotels. Quite often the systems are not very well balanced, and you end up setting your cooling at, say, I don't know, 20 degrees C, when actually a comfort cooling should be around 22 to 24, depending on your depending on the building and space you're looking at. And for 1 degree too low room temperature in the summer, we can be looking at 12 to 18%. So we can be looking at some serious numbers in terms of energy consumption, in terms of going for low energy usage from an environmental perspective, but also on that's straight on my OPEX. My operational costs of my building are going to increase dramatically for what is effectively only a small change in set point due to a lack of balancing. So that was an overview on why should we balance? Where are these costs associated there? What I want to look at is actually some of these sources of imbalance here as well. Now, if we look at sources of imbalance, I'm going to start now talking about coming away from flow and actually talking about differential pressure. And if we look at this system here, so we have a cooling system here serving a number of floors, a number of risers, and a number of emitters. These could be, say, fan coil units on each floor. I have a pump here in my plant room providing a differential pressure. It is providing a difference in static pressure between the inlet and outlet of the pump. What then happens is my water flows in my systems are going to establish themselves in function of the relative resistance of the branches in respect to each other. So as I said before, water is fundamentally lazy. We have a higher available differential pressure at the inlet of the system than we have towards the extremes of the system. So invariably what then happens, we end up with overflows towards the start and underflows towards the end. And that's because we have a relative, if this system we had 4 identical risers for the sake of argument, but because of my distribution network, we are losing differential pressure in my piping. My sources of imbalance being my pipe losses, they are the main, to be honest, one of the main losses in a system is my pipe work and associated fittings. They are going to be causing these differences in available pressure to each area. And therefore, my difference in available pressure is going to have a dramatic impact on my flow. And the same thing happens at a terminal level. So on each floor, again, we can have excessive flow on the units closest to the inlet. And as we go further out on that floor, we have larger pipework resistance. We're going to get a consequently lower flow rate. So the question is always, how do we obtain the design flow in every terminal unit to stop something like this happening? And this is a hotel here where you can see on this side of the hotel is freezing cold, and here we're overheating. We've got windows open on the side of this side of the hotel. So we're going to see here some huge imbalances in action. And how do we do that? And that's actually where the balancing valve comes in, because most of these imbalances are due to the difference in pressure loss for different sections of the pipe, because we are losing pressure as we go down there. So the idea with a balancing valve is we wish to adjust the local hydronic resistances, absorbing the excess differential pressure to obtain the required flows. Now that sounds, in a sentence, you could say that sounds fairly simple, but we're going to look at how we do that during there. And the idea with this is we're going to be using a manual balancing valve. And what a manual balancing valve does, it allows me to adjust my resistance and physically measure the flow that I'm adjusting to. So I can, with a manual balancing valve, adjust this valve to take out the difference between the flow going here or the flow going up here. And I can make it so that I effectively force the water further down my system by making it more difficult relatively to go up that first riser. As I said, water's fundamentally lazy. You take the example of if I took a park, big park, and there was 3 routes through this park, 2 long ways around the outside and a shortcut through the middle. All open, all easy to walk down. And I took 100 people and I said, right, I want you to get from point A to point B. If I wanted an equal split, I would need to make it just as difficult or just as long to go through the middle, the shortcut, as it is to go around the outside. And in essence, that's what the balancing valve does. These have been around for quite some years now, some 70 odd years. Actually, the original idea came from Tura and Agentura back in 1953, later became Tura and Anderson, part of the IMI group now. And the first patent balancing valve was received in 1962. So it's by no means a new product, by no means a new concept. And this is those sources of imbalance there that we are looking at to ensure here we obtain the correct flows throughout the system. Next, I want to actually look at flow itself and how is flow produced in a system. And really importantly, I want to put a large importance here on the differential pressure, with the differential pressure being the difference in static pressure between 2 points. So if we take this very simple loop here with a pump, a control valve, a terminal, and a balancing valve, we have a starting static pressure here that is set by my static pressure vessel on the inlet side of the pump. And here, the flow in the circuit is only depending on the differential pressure. It is only the differential pressure in the circuit that does this, not the static pressure, the difference in static pressure. And in my system, pumps are going to increase that pressure while other components will decrease it. And actually, in hydronic circuits, the only important pressure is therefore the differential pressure once pressurization is properly ensured. Because if we look at this system here, if we said at design conditions to have the design flow through this system, we have a pump. And let's say we started at 150 kilopascals. My pump adds 100 kilopascals. 150 to 250 is 100. I then have a control valve, and that is removing now 35 kilopascals. 250 to 215. I have a terminal that is this now removing 40 kilopascals. 215 to 175. And finally, the job of the balancing valve is to remove that last difference of 25 kilopascals to go from 175 back to 150, because we must start again at the same pressure, the same static pressure as we started. We cannot have a difference in pressure between, in this example, there's no pipe work resistance to simplify it. We must have the same starting point here. And again, let's look at this same example with a different starting point, starting at 200 kilopascals. Once again, my pump increases the static pressure, going from 2 to 300 kilopascals. It's that same 100 kilopascal difference. My control valve, again, takes out 35 kilopascals, 300 to 265. My terminal unit takes out 40, 265 to 225. And finally, the balancing valve is taking out that 25 kilopascals, that extra piece to bring me back to 200 kilopascals once more. And it is this difference in pressure that is driving flow through the system. But how does it drive flow? What is the relationship between flow and differential pressure? That's what we look at here. And if we take pressure drop versus flow, in valves, in pipes, in terminal units, the relationship between the flow and the pressure drop for a turbulent flow, which when we are talking HVAC systems at design conditions, which is what we're balancing to, we should have turbulent flow throughout the system. It should have been designed and sized correctly for turbulent flow. The differential pressure is proportional to the square of the flow. So this is my inverse square law. So that means if the flow is doubled, the pressure drop is multiplied by 4. 2 times by 2 is 4. And we have this inverse square relationship. So this is the relationship between differential pressure and flow in a system. The steeper that relationship is, the less capacity for flow the system has, i.e. the more differential pressure you require on that system or that part of the system to obtain the flow you desire. As some examples here. Now, this is a really important relationship when we're talking about balancing, because we really need to understand how the differential pressure is having a key influence on the flow here. So if, for example, I would like to increase my flow by 15%, you might say, well, yeah, that's only a relatively minor increase. That's maybe going up 15%. We actually, for that case, we would have to increase the differential pressure by 115% squared, or 32%. So to get a 15% increase in flow, we require a 32% increase in differential pressure. Now, bearing in mind what is the only component that increases differential pressure in a system? Valves can't do it, pipes can't do it. It is only the pump that is creating a difference in static pressure, i.e. we'd have to increase my pump head by 32% to get my flow up 15%, which that could be due to poor balancing that we have to do that increase. Conversely, if we said, okay, I can only increase by 20% on my pump head, a 20% increase in differential pressure leads to a flow increase of 120% to the power of 0.5, or the square root of 120%, i.e. a 10% increase in flow. So due to the inverse square law, a 20% increase in differential pressure only leads to a 10% increase in flow. Now, for those of you that may be a little bit more comfortable with electronics, we could put these parts akin to some different parts of the of Ohm's law, where my differential pressure is equivalent to my voltage difference, and my flow is equivalent to the current. The key difference being, in Ohm's law, it is a linear relationship. So a 50% increase in voltage leads to a 50% increase in current, and vice versa. With the inverse square law, we have this square relationship, where the differential pressure is proportional to the square of the flow. And we can apply that as a general rule. And this is the inverse square law. So this is a simplified version of the relationship of flow and differential pressure of any component in a system under turbulent flow, where flow is in meters cubed per hour and differential pressure is in bar. We can say that the flow is equal to the kV. Now, the kV is the capacity for flow. Going back to our electronics, that is equal to the resistance. It is the inverse, actually. So a higher capacity for flow directly leads to a higher flow for a given differential pressure, or a lower differential pressure requirement for a given flow, multiplied by the square root of differential pressure. And the simple way we can look at this kV as a function, in essence, it is a function, if we break it down, that is equivalent to the area inside that device. So a valve, the smaller the area is, the lower the capacity for flow is. The smaller the restriction is, the lower the capacity for flow, which, if you think about it, makes sense. I would need a higher differential pressure across a piece of equipment if it was of a smaller opening than a larger opening piece of equipment. And actually, kV in terms of measuring, what often happens is we would set a differential pressure of 1 bar across a piece of equipment, say a valve, and we would then measure the flow with a separate measurement device in meters cubed per hour, and that would be equal to the kV of that piece of equipment. The flow would be equal to the kV, because if the differential pressure was 1 bar, the square root of 1 is 1. So we can then say the flow is equal in meters cubed per hour is equal to the capacity for flow, or kV, of that device at a 1 bar pressure drop. And as I said, that is a simplified relationship for water at 4 degrees C, because it is also including the density of water as a factor here, where at 4 degrees C, the density of water is 1000. So that is a brief introduction to the inverse square law and the flow versus differential pressure requirements of a system. And it's really important to bear that in mind when we're looking at systems, to see, okay, just a small increase in differential pressure is going to have a very small increase in flow, or vice versa. If I wanted a 20% increase in flow, that's not going to be 20% increase in differential pressure. That's going to be the square of that increase. So it's going to be around, I think it's 40%. So that's some of the sort of the relatively straightforward engineering mathematics behind flow versus differential pressure. What I want to look at now is look at something called the proportional rule. And the proportional rule is something that, if you have ever done any balancing in your careers, or had any influence on balancing, something that you will have already seen, but you may not realize that you have. If I take a module and I would like to balance it, if I was to iteratively, i.e. trial and error, we quickly become a nightmare. So if I now take a look at a simple module here, where we've got a setup here with 5 different modules, and we want to get them all to 100%. So let's say, okay, right, let's push my pump. I can see now this one isn't here. This one isn't quite at 100%. So I can push my pump up here to try to get to 100%. And we can go, right, cool, I'm happy with that. But I've seen here, this one's at 268%, so let's start to close that down. To get that down to around 100%. You go, hang on. Oh, this one's gone up now, so let's time decrease this one. Bring that down again. And you can see I'm able to see the flow in all 5 of these pretty easily. And let's come back up again. Let's decrease that. Okay, we're good. This one's at 200%. Try and adjust this down. And we can see flows are changing throughout this system in what seems a fairly, if you've not been paying 100% attention, fairly random manner. And iteratively, it can become a real nightmare to try and set this system up. We're having to scope between 5 different devices. And as I said, relatively speaking, this is pretty easy because I can see live the flow in all of these 5. And how often are you balancing a system with only 5 devices on there? Very quickly, we're getting to a stage where we're just throwing stuff at the wall and hope it sticks, and just, come on, we're still at, this is now 115%. Let's close this down. I've gone a bit far there. Let's push that back up again. This one's still at 150. Let's shut this down. And you can see we can get somewhere where we're going to need, and let's get there. See what we're looking at. We're back at 130% now. Drop that down to 100%. There, a bit far. Okay. I'm going to say, right, I'm happy with that. That's balanced. I've got between 100 and 108% throughout there, iteratively. It's been quite a nightmare. I've had to keep switching back and forth. And actually now let's have a look at my pump consumption. In terms of consumption, this is running currently at 180% of the optimized setting. So i.e. when we are using nearly twice the pumping energy we need to get the flow to the right area on this pretty simple system. And what we're going to look at now is something called the proportional rule. Now, the proportional rule is a really important thing with manual balancing. Let's take an example here where we have 100 flow units here, or 100% of flow. And we have a split of 30, 20, 10, 20, and 20. If I wish to exploit the proportional rule states that any change I make upstream affects all units downstream in the same proportion. So if I adjust this valve to 150, we can see magically, i.e. a 50% increase. We've had a 50% increase in flow in each of these 5 units. 30 to 45, 20 to 30, 10 to 15, 20 to 20, 30, and 20 to 30. So I can show that again as an example. If we click back to here. So we're all at around 100%. Let's try to make it a little bit better so we can exploit it a bit further. Let's drop this one down a little bit. Okay, we're all at 100% now. And now let's push my pump head up here. And let's increase. So increasing the pump head is, we can see, for the sake of argument, they've all gone up 20% in proportion to each other. That is proportional rule number 1. That's for me, when I first learned, that was a pretty easy thing to understand. If I push the differential pressure up throughout the system, the flow increases in proportion on all of those units. Proportional rule number 1, pretty simple. Actually, it also applies itself downstream from a change. So if we take this again, this simple system here with 5 units or with 10, a flow of 10, let's say this is litres per second, pretty big system, 10 litres per second in each unit. If I shut this middle unit downstream of this change, I get the same proportional increase in flow on these two, but upstream, I don't get the same change. So what that is then really useful for using is we can exploit this proportional rule, and we can actually exploit it when we're wanting to balance. So if we come back to my unit here, and I'm going to cheat, I'm going to go off and then go back to fully open again, hopefully. It's not done it. Push these all up. It's going to take a while. Let's do it the easy way. Let's close it and open it back up again. Okay, fantastic. My computer is obviously on a go slow right now, and it has not changed it. That was a waste of 2 minutes. There we go. Let's push this up anyway. Let's get them all back to fully open position so we can start the process all again. But this time I'm going to exploit the proportional rule. And again, I want to point out at this point that actually I'm making it really easy for myself because I can see what's happening to the flow in all of my units live as we do this. So let's turn this off as well. Come on. Apologies, this is the sort of demo we'd always like to do on a real test rig, which is a lot simpler because I can just quickly move some hand wheels instead of relying on an Excel formula to update. And as ever, these things go slowly when we're being watched. Okay, brilliant. We are back to, let's push this pump head back down. Let's get ourselves back to 100% on this last unit, or there or thereabouts. And I'm now going to exploit the proportional rule. So what it's going to state is any change I make upstream affects all units downstream in proportion. So in essence, what I want to do is I wish to change units downstream until I get these two units in proportion to each other. So now I'm going to reduce the opening here until these two units in proportion to each other have the same flow, or as close as we can get it. Okay, I'm happy with that. 105 versus 104%. And now we're going to take this unit in the middle and we're going to restrict this unit down as well. And what we're going to do is I am going to reduce it until these are the same. And if you look now, all three are the same. Turn this bit off. All three are the same, and these two have changed in proportion as I've done this change here. And again, we go back upstream one more unit. And this is if you've ever done any commission, this is why you will always commission from what we call the index or reference unit back towards the pump. It's because of this proportional rule, but we can actually see it in action here. So again, let's try. Okay, 18%, and these are all increased a little bit. And then finally, let's take this last unit and let's reduce the opening here till we get everything in proportion to each other. So around about 130%. We go, okay, I'm pretty happy with that. And you can see we're at 130% of design flow in all areas. Now, this is a pretty simple system. Directly, my pump is serving this one system. So actually, I can just then reduce proportionally by reducing my pump head. If we reduce my pump head until we get 100%, turn on my little pump consumption, as if by magic, as you may well have expected, we are now back to 100%. My pump has been set and optimized. And you'll notice this guy here is actually fully open because we've done my final setup on the pump. We could do it another way, and we're going to look at why we may need to another option. So let's put me back here. We could do the same function by decreasing the opening here, increasing this differential pressure, and in proportion, we have now balanced my system. But again, we're running at 180% more energy than we need to, because as you'd imagine, look, we've got 60 kilopascals in this valve, which we could effectively take out of the pump. But that does not mean that valve should not be there. And what we're going to look at now is I'm going to introduce to you what we call the hydronic module. And this is the last section of the webinar today. So looking at my watch, we should be able to get it in there. So we're going to look at the hydronic module. And the hydronic module is what we call the building brick of the system. And what is a hydronic module? Now, we've already seen them in actuality on a few of the options we've seen here. We want to have one balancing valve per circuit or unit. Pretty simple and straightforward. We want to measure the flow on all of my fan coils or my air handling units or whatever these devices are. So we're going to want to put a balancing valve on there. Nice and easy. We also need to use something called direct return piping. Direct return piping means we flow into the unit and directly return back. And this is really important if we want to proportionally balance. We must have direct return piping to exploit that proportional rule. If we run what's called reverse return, which is often used, and if in our full courses we show why reverse return doesn't work, headline figure, it's not a great solution, we would not be able to exploit that proportional valve. And finally, we want to have a main balancing valve called a partner valve or compensation valve. And we're going to see in this hydronic module setup why this valve is really important, because this is going to have a real purpose there. So let's, in the next sort of last 5-10 minutes or so before we open up the Q&As, have a look at splitting a system into modules. So here we have a fairly typical hydronic system that we've got a number of devices. These could be fan coils or air handling units or process cooling, or could be a data center, whatever it is. We don't really care, just a representation of a system. And the first thing I always recommend is, if you're fairly new to this, and still to this day, if I look back in my pad, I was doing some work yesterday for one of my colleagues in the UK, Friday for one of my colleagues in the UK. I want to simplify this drawing. Really important thing. First thing to do is simplify that drawing. Take out any strange things of how it's drawn and just do it really simply. And because we're running a direct return system, we can represent the flow and return pipe for this exercise as a single pipe. So this pipe is representing the flow and return, serving each of these units. Simplified my drawing, making it nice and easy. But the question here is, how do we split this more complicated system than we've been looking at so far into hydronic modules? This system could actually, and quite probably, would form part of a larger building. In this example, we've got 3 floors, all with identical setups. And when we are splitting into hydronic modules, the easiest and safest method is always to start from the pump. And the way I like to talk about this, and the way when I'm training people we talk about this, is imagine you had a bag full of balancing valves. And let's say you can either imagine you were really, really tiny or the pipework was huge, whichever way suits your imagination better. But for me, I like to imagine I was very, very small with a very tiny little bag full of balancing valves. And you can then think about walking down the system. And we're going to start here. We're going to start at the pump. And the first thing we want to do is we want to place a main balancing valve by the pump. Now, you might say to me, yeah, Rob, but I thought we said we want to only add the absolute resistance we really need. Why are we putting a valve in series with the pump? Because we could just adjust the pump. But that is a key point to put there because it simplifies our commissioning and allows us to do fine adjustments and measure the total flow in the system. What we then do is we follow the path of the main flow in the system. And as we can see here, the main flow is going to carry on up the system. And at every takeoff, anywhere where the main flow is not going, we place a manual balancing valve. So we place a manual balancing valve on the floor here, and finally at the end here. We then say, if there is only a terminal unit at that takeoff, that's final. So if that up here was serving a single air handling unit, that's final. We don't need to do any balancing downstream of that unit because all there is that particular air handling unit. But if there's more than one terminal unit at this takeoff, we designate it as a sub-module. And we mark this manual balancing valve so we know it's not final and we know it's a partner valve. And the safest method is always to do this process starting from the pump methodically, following the path of the main flow, placing a balancing valve and carrying on up the system and marking those balancing valves where you need to go and revisit, and you take out that exact same process in this example on a floor. So we're now going to look at the main module on the floor. We get to this point here. We can go left, right, or straight on. The main flow is going straight on. So we place a balancing valve on the left and the right. We have the same scenario here. The main flow is still going straight up. So we place a manual balancing valve on this unit on the left. A little bit more complicated at this intersection. Is the main flow going to the right or is it going straight up? Now here we need to know something about the flow in these units. Now for the sake of argument here, we're going to say all of these units are identical to make our life 10 times easier, and I don't need to know the flow. But if we were working with drawings, on the drawing itself, it should be written what the flow is. So the main flow is still going to be carrying on up the way. So we place a manual balancing valve on the right hand side and we carry on to the next intersection. Here we have the option to go left, right, or straight on. And we're going to place the manual balancing valve on the left and we're going to carry on to the right. And you'll notice we follow this down all the way until we get to the end of the system. One key thing to notice, and I want to point this out at this point here, we don't need a manual balancing valve left and right. We just follow the path of the main flow in order to optimize both capex, how many valves we need to buy, and opex, minimizing my pumping costs. We do not want to end up putting valves in series with each other. So therefore, we do not require a valve here. And you'll notice in this example, we've got 3 valves that are also submodules. So we carry out the same operation on the submodules. In this case, it's really simple. My submodules just have terminal units, so we place the balancing valves on each of these terminal units. We do the same process here. And finally, we do this process at the end there. And we have now correctly identified the optimal number of manual balancing valves we need to manually balance this system in the most optimized way. And in this example, we have a floor with one main module and then 1, 2, 3 sub-modules running off there. And the idea with this is we then know we can set these 3 valves to here. So you can really see the idea of the partner valve. We can set up, okay, proportionally, let's set up here. And when I adjust this valve, the flow increases in this valve and this valve also. But then when I adjust this one, we know the flow that increases here is the same as an increase here. So therefore, I only need to measure this valve and measure what the increase happens as I restrict this. I can get these 3 valves proportionally balanced. I can then do the same function on these 3 and on these 4. And then I know via the proportional law, when I adjust these 3 partner valves, my modules will also be adjusted in proportion. So all of the valves in the module. So in essence, if I want to balance this system, the first thing I would do is here, so then here, then here, and then I can balance this main module back, the partner valve on the floor. I can carry out that exact same exercise on all of my floors, and then finally balance the floors against each other, again exploiting the proportional rule and ensuring I have optimally balanced that system and made the system operate 100% of design flow in all areas whilst adding the minimum amount of pressure drops. So that is all for this morning's webinar. Thank you very much for joining. Next webinar, we are going to be looking at some of the advanced manual balancing methods. So we're going to follow on from today, and we're going to look at how we can actually utilize the proportional law in some really more advanced manual balancing methods using our TA scope. If I could ask you, if you could take a scan of this QR code, it should hopefully take you to a survey where you can provide some feedback on today's session. But that is all for today. Looks like we've finished in a very nice time with about 10 minutes to go. So what I shall do now is I will have a look and see if we have any question and answers in the chat. So let's see, do we have any Q&A there? There's no Q&A. Okay, fantastic. Does anybody have any burning questions? You should. Let me see. How do we do this? Controls. I've now allowed you to turn on your cameras and unmute yourself. So if you have any questions on the material we've covered today or the material we're going to be covering in the future, please feel free to unmute yourself. I'll give you all a couple of minutes to do so. But if there's no further questions, once again, thank you very much for joining today. And I hope you've enjoyed the webinar.
Thank you very much.
Thank you.
Thank you, Rob. Very well done.
Cheers, Simon. Recognise that voice. There might be something there. Okay, fantastic. Well, looks like we have no further questions. So either I've done a good job and everybody's learned something, or everybody's bamboozled and there's no questions. But once again, thank you very much everybody for joining, and I will see next session will be on the 18th of November, so just under a month's time. Same time, so 9 o'clock in the morning in Australian Eastern Time. Thank you very much for attending. Looks like we've had a good number of attendees, and I wish you all a fantastic rest of the day.
Thanks, Sean. Much appreciated. Cheers. Bye.
Thank you.